Lesson 20, Putting Compounds into Reactions. The objectives for Lesson 20 are to explore how compounds react with each other and to learn skills for writing chemical reactions. In Lesson 19, we discussed the rationale for learning the skills of writing empirical formulas. We said that in the process of creating new products for consumer use, many byproducts were also produced. We discussed that the analysis of these products and byproducts was essential to determine their potential usefulness and possible methods for disposal. In this lesson, we will begin to explore the basic concepts of how chemical compounds interact with each other. We will also discuss how we can record what happens in these interactions in order to share this information with others. To facilitate our discussion, let's use an analogy. In your life, you have very likely encountered several situations in which you had the opportunity to make new friends. These situations may have been as simple as making a new friend at the merry-go-round on the playground, or as exciting as meeting a companion who could be the one to share your life adventure. These situations can range from being uneventful to quite eventful. For example, you may make casual conversation with a young man or lady who carries your groceries to the car and never get past phrases like, "It's really a nice day," or "Thanks for not squishing the bread." However, in other situations, your interaction with another person may be much more eventful, and a conversation may grow into a lifelong friendship with discussions of very meaningful topics like goals, dreams, and aspirations. The range of interactions between chemical compounds is just as wide. The interaction varies from being almost incomprehensible to the very intense and even explosive. Some interactions may be very slow in developing, and some may be instant. Let's begin by introducing some terms which are used by chemists to describe a chemical interaction. First of all, the interaction between two or more chemicals, whether they be single elements or compounds, is known as a chemical reaction. The participants in a chemical reaction, that is, those chemicals that have found themselves in a situation in which they can interact with each other, are known as the reactants. The chemical nature, or in other words, the reactivity of these reactants determines whether a reaction will take place. What results from the reaction are known as the products of the reaction. Recall from our earlier discussions how the arrangement of electrons in an atom's electron cloud determines the reactivity of those atoms. Recall that all atoms have a tendency to seek the stability of a noble gas. By taking the opportunity to react with another chemical, whether it be a free element or a compound, a reactant might have a chance at acquiring a more stable configuration. You might compare this idea to that of two talented musicians, one very gifted in playing the bass guitar and the other quite talented in playing the lead guitar. By themselves, they may be limited in their performance, but together they can produce quite an outstanding presentation and possibly be more satisfied with their performance. Likewise, reactants interact with each other in an attempt to acquire a more stable, satisfying electron configuration. Let's go back to our terms. We stated that the reactants were those chemicals that were exposed to each other in an effort to lead to a reaction. The results of this reaction are known as the products of the reaction. The products are those chemicals, whether they be free elements or compounds, which result after two or more reactants interact with each other. In order to say that a chemical reaction has taken place and new products made, there must be evidence that a chemical change has taken place in the reactants. In our analogy, we might say that a reaction has taken place when our thoughts or ideas change as a result of interacting with our new friend. The evidence of a chemical change varies according to the reactants. The results that are generally considered evidence of a chemical change are that a change in the chemical properties of one of the reactants has occurred, there's been a change in the solubility, in other words, how well a substance dissolves in another substance of the reactants, or a change in the color of the reactants. An example of a change in the chemical properties of the reactants, which is evidence of a chemical change, is how the properties of the free element sodium change drastically when it reacts to form sodium chloride, commonly known as table salt. Recall that sodium, which is atomic number 11, has one lone electron in its outermost energy level, and will readily lose that single electron to acquire the stability of its noble gas neighbor, neon. Because of sodium's very strong desire to lose that single electron, it is an extremely reactive element. These explosive properties are radically changed when the sodium cations form the ionic bond with chloride anions to make sodium chloride. Recall that chlorine is a member of the halogen family and has the desire to accept one electron to achieve the stability of the noble gas family member neighbor, argon. Sodium chloride, as you well know, is a very stable compound. You can heat table salt, nothing happens. You can mix it with almost anything, and very little happens. Most people can eat table salt, and nothing happens. This drastic change in chemical properties, which is sodium's change from being highly reactive to being very low reactive, is very apparent evidence that a chemical change in the reactants has occurred. The presence of a color change as evidence of a chemical change can readily be observed when jewelry, often made of copper, turns your skin a greenish-blue color. The reaction between the substances on your skin and the copper jewelry causes the copper to change color. Another example is the whitening characteristics of sodium hypochlorite, commonly known as chlorine bleach. You may have had the unfortunate experience of having bleach splashed onto your favorite shirt or jeans. The resulting white spots are evidence that a chemical change has occurred. Scientists who use hydrogen peroxide to whiten bones of an animal skeleton before they put it back together witness a chemical change too. The simple reaction of a piece of metal rusting when exposed to moisture, which is the color change of silvery gray to reddish brown, is yet another example of a chemical change. Detecting a change in solubilities as evidence of a chemical change may not be as commonplace around the house as detecting changes in chemical properties or color changes. You may have experienced the chemical change which occurs when you mix vinegar with baking soda. The reactants here are the acetic acid, which is vinegar, and sodium bicarbonate, which is the baking soda. The bubbles which result are filled with carbon dioxide gas, which is no longer soluble in the vinegar, and rise to the surface. This change in solubility is evidence that a chemical change has taken place. Another example of a change in solubility is the preparation of cheese. As vinegar is slowly added to warmed milk, the milk proteins clump or coagulate and no longer are evenly dispersed in the milk. These clumped milk proteins form the cheese and the remaining liquid forms the whey. In the chemistry laboratory, this formation of an insoluble product is known as precipitation. The insoluble product, in this case the cheese, is known as the precipitate. Creating a precipitate is one way chemists can separate chemical compounds. Now, not all reactants immediately begin reacting once they are exposed to each other. Some reactants, like shy individuals, may need to be introduced to each other and some energy applied to the situation in order to get things rolling. This needed energy may be as simple as a gentle shake or stir, or as complicated as application of external heat or even an electric spark. For example, when baking a cake, the recipe requires that the ingredients are vigorously stirred or beaten. This is done to ensure that the baking powder gets exposed or introduced to the other ingredients, which results in the formation of carbon dioxide bubbles, which causes the cake to rise. Another example is the heating that is required to make candy, such as peanut brittle. In order for the sugars in the candy to chemically change, heat must be applied. Other examples are photoflash bulbs. A tiny spark of electricity is applied to a tiny aluminum wire inside the oxygen-filled bulb. The aluminum wire is ignited and reacts vigorously with the oxygen to emit an intense flash of light. Without the spark to get the reaction started, nothing will happen between the aluminum wire and the oxygen. In other words, energy may have to be applied to a set of reactants in order for a reaction to get underway. Some reactants require that energy be continuously applied for the reaction to continue, whereas others may only need a little initial energy to get things started. An example is the simple kitchen match. The heat generated through the friction of striking the match is all that is needed to get the phosphorus on the tip of the match to react with oxygen in the air. Once the reaction is started, the remaining chemicals in the match begin and can continue to react, including the wood, which undergoes obvious chemical changes. Reactions which require an input of energy in order for the reaction to get underway are known as endothermic reactions. The prefix endo means putting in, and the root word thermic means heat, as in thermos or thermostat or thermal blanket. You can see that the term endothermic means that heat or energy must be added to the reaction for it to commence. The energy that is put into the reaction may be stirring, shaking, heating, or applying electrical or light energy to the reactants. On the other hand, some reactants produce or release energy as the reaction proceeds. The energy that is released may be in the form of heat, light, or sound. These reactions in which energy is produced or released are known as exothermic reactions. The prefix exo means leaving or exiting, and again the root word thermic means heat or energy. Together we have the word exothermic, which indicates that energy is leaving the reaction. There are many examples of exothermic reactions. The process of burning or combustion is an exothermic reaction. The process of striking a match may be endothermic reaction, but once the reaction has begun, the remaining reactions are exothermic. Energy in the form of heat and light from the flame of the burning match are evidence of an exothermic reaction. Burning a candle and the filament in a light bulb are also examples of exothermic reactions. The gasoline and oxygen reaction in an automobile engine is quite an exothermic reaction. A tremendous amount of heat and sound energy are released. In the process of making lye soap, the lye crystals, which are sodium hydroxide, must be dissolved in water. The lye reacts with the water, producing a large amount of heat. The soap maker must be aware of this heat production and allow the mixture to cool before mixing it with the fat or tallow to make the soap. In addition, the use of lye or strong acids such as sulfuric acid to open clogged drains can be an exothermic reaction, and all precautions on the drain opener label should be followed closely. Here are some descriptions of chemical reactions that you may not be familiar with that can be performed in a laboratory. See if you can identify them as being endothermic, exothermic, or maybe both. Here's the first one. When hydrochloric acid and water are placed into the same container, the container becomes very warm and sometimes even hot to the touch. Is this reaction considered endothermic, exothermic, or both? If you said exothermic, you're correct. Here's another example. When magnesium ribbon, which is a form of the element magnesium which has been flattened into a narrow ribbon-like strip, is heated with a match, the magnesium begins reacting with oxygen in the air to give off light so intense that it can damage your eyes if observed directly. In addition to intense heat, can also be felt near the reacting magnesium. Is this reaction considered endothermic, exothermic, or both? I hope you said both, because it was endothermic reaction when the magnesium ribbon was heated with the match, but then exothermic when the light and heat were produced. Here's a third example. An interesting reaction takes place when barium hydroxide and ammonium chloride are stirred together. As reactants, they are both white crystals, but as they are vigorously stirred together, they become a colorless liquid. If the beaker or container in which the reaction is taking place is placed over a puddle of water on a wooden block, the water quickly freezes, causes the block to become adhered to the bottom of the beaker or container. Is this reaction considered endothermic, exothermic, or both? This reaction is considered to be endothermic, both when mixing to get the reaction underway, and then following as water freezes beneath the container. When making new acquaintances and friends, we, like some reactants, may be permanently changed into a new product. On the other hand, we may only be temporarily altered and soon return to our previous state. We can say that some chemical reactions are reversible and some are irreversible. To indicate when a reaction may reverse or is unidirectional, irreversible, we can utilize a system of notation to represent chemical reactions. To describe what is happening in a chemical reaction, we can write the reaction using words or symbols. The written description of a chemical reaction, whether in words or symbol, is known as a chemical equation. Let's look at some examples of chemical equations. When hydrogen and oxygen are placed under appropriate conditions, water can be produced. To write this reaction in words, we might say, hydrogen and oxygen react to produce water. We can write the same chemical reaction using symbols. The chemical formulas for each reactant are written using an addition or plus sign to indicate that the chemicals are being combined. To indicate that a chemical reaction has taken place, an arrow is written following the reactants in the direction of the products, which are written to the right of the arrow. Let's look at the hydrogen and oxygen reaction written now using symbols. Hydrogen would be H2 plus oxygen O2, the arrow sign, which we might say as reacts to yield, the water, which is H2O, the product. Note that the reactants are written to the left of the arrow and the products are written to the right of the arrow. To indicate if the reaction is irreversible, a single arrow is used. If the reaction is reversible, two arrows are used, one in each direction. Here's an example of a reversible reaction. Hydrogen and iodine react to produce hydrogen iodide. So we would write H2 for the hydrogen, the plus, which indicates that it's being mixed with the iodine, which is I2, and then we have arrows going both ways, and then the product, HI, the hydrogen iodide. In addition to writing the reactants and products, we can also use symbols to indicate the phase or state that each component is in during the reaction. The three phases of matter that we are referring to are solids, liquids, or gases. To indicate these states of matter in the equation, the symbol S is used to indicate a solid, the symbol AQ or L is used to indicate a liquid or aqueous form, and the symbol G to indicate a gaseous form. Here's an example. Gaseous nitrogen dioxide and water react to produce liquid nitric acid and gaseous nitric oxide. So on our reaction, the gaseous nitrogen dioxide would be NO2 with a small g next to it, and the water, which was liquid, so we'd have H2O with a little L, the arrow to indicate that they are reacting to produce the liquid nitric acid, which would be the HNO3 with a little L next to it, and, again a plus sign, gaseous nitric oxide, which would be the NO with a little G following it. If certain conditions are required for the reaction to take place, those conditions can be written over the arrow in the chemical reaction. For example, the word heat may be written over the arrow, or the specific temperature can be written if it is known. Here's an example. Solid ammonium nitrate reacts at 200 degrees Celsius to form gaseous nitrous oxide and water. In our reaction, we would have our ammonium nitrate, which is NH4NO3 with a small s indicating that it was a solid, reacts, we would have our arrow, and above it we put the 200 degrees Celsius to form gaseous nitrous oxides, we'd have the little g following the N2O and a plus sign, the water, H2O, with a little L to indicate that the water is in the liquid state. Another notation that can be written over or beneath the arrow is to indicate specific reaction conditions, is the word catalyst. A catalyst is a substance which is added to a reaction to increase the speed of the reaction. The catalyst itself, however, is not changed in the reaction. Look at this example. Sulfur dioxide gas and oxygen gas will react under heat and in the presence of a catalyst to produce sulfur trioxide gas. So in our reaction, we would write SO2, which is a sulfur dioxide gas, using a little g, and oxygen, so we're going to put the plus O2 with a small g for our gaseous oxygen. It says it will react under heat, so we're going to draw the arrow and above it write heat, and then it said in the presence of a catalyst, so we would write the word catalyst there, to produce sulfur trioxide gas, so it will be SO3 with a small little g following it. As we continue working with chemical reactions, we will come across certain elements which are gases at room temperature and like to exist as two-atom pairs. For example, oxygen gas at room temperature likes to exist as O2, which means it has two atoms of oxygen existing as a pair. Gases like oxygen gas are called diatomic gases, where the prefix di refers to two. Therefore, we have the term two-atomed gases, or diatomic gases. In addition to oxygen gas, there are several other diatomic gases. The diatomic gases that you will encounter in this course, as we've already said, is the oxygen gas is O2, hydrogen gas, H2, chlorine gas, Cl2, bromine gas, Br2, nitrogen gas, N2, and iodine, while it's not a gas at room temperature, it's actually a solid crystal, it still likes to exist as being diatomic, or I2. Let's review what we've learned in Lesson 20. The components which go into a chemical reaction are called the reactants. The components which are the result of a chemical reaction are called the products. Evidence of a chemical reaction include a change in the chemical properties of the reactants, a change in the solubility of the reactants, or a change in color of one of the reactants. Reactions which release energy are known as exothermic reactions. Reactions which require energy to get underway are known as endothermic reactions. When writing reactions, arrows are used to tell the direction of a reaction. Practice writing chemical equations now by referring to the practice pages at the end of Lesson 20 in your student textbook.